Bismillahirrahmanirrahim. Assalamu alaikum dear students. Welcome to the online lecture on MATLAB simulation of control systems. Today we are going to discuss super twisting sliding mode control design for electric dynamic load simulator. This paper has been published in the proceedings of 38th Chinese Control Conference in 2019. So without further delay, let's get into the action. So as usual, I'm not going to go through the details of the paper. Rather, this video is going to be about how to interpret and simulate the control and dynamics related equations of this paper in MATLAB. So the whole schematic representation of electric dynamic load simulator is given in this diagram. You can see here that there is a permanent magnet synchronous machine driver, and then there are some gearing mechanisms, and then there is torque sensors and electromechanical actuators. And then these actuators also have their own drives, and then there are controllers behind. So this is the practical implementation. At the end of this paper, the authors have also shown some practical setup that they have used. So the whole story of the paper is that you have electric dynamic load simulator where mathematical model of the permanent magnet synchronous machine, that is a second order system. Rate of change of angle is the angular rate, angular velocity, and the rate of change of angular velocity is proportional to the sum of all the torques acting on the machine. Then dynamic equations of the electromechanical actuation servo system, that is very similar to the one above here. And the main system that is under discussion in this paper is this load torque system, where x1 state is the this load torque, and then x2 state is the derivative of this torque, and the output is the torque itself. So input u is some scaled version of the input that we can discuss later on, although this discussion is not going to come a lot in the simulation that we have discussed. We can basically because the final control law given later on in the paper is directly in the form of u, so we can just skip somehow, or otherwise if there is a typo in the paper, then we need to multiply k1 with the u, which should not be very difficult, because k1 is just a constant given by kg km over n times jm. So this constant is given in the paper. So state space model is quite simple. x1 dot is equal to x2, x2 dot is equal to u plus phi, where phi is the sum of two functions, f of x and this phi of theta l. F of x is minus k2 times x2 minus k3 times x1, and phi l is minus k4 times theta l double dot minus k5 times theta l dot. So k1, k2, k3, k4, k5, they are all given in the paper, so we don't have to worry about this. Now they discuss the super twisting sliding mode control. Before discussing that, they also discuss the PID control. This is basically the PI control, where we have the controller has proportional gain and the integral gain, which depend upon the output function. We will, in the end of this video, will also compare the sliding mode control with the PID control. So for super twisting sliding mode control, we have first of all we define the error. The error E1 is the difference between the reference value of the torque and the actual value of the torque, and the error E2 is the difference between the derivative of the reference value of the torque versus the actual value of the derivative of the torque. And then these are the dynamics of the error, and this is the sliding surface, which is of high interest to us. Sliding surface S is equal to E2 plus C times E1, where C is a positive constant. Then they have also provided some diagram which will help you in simulating this whole thing in the Simulink. I will also show you a Simulink diagram which is created based on this this figure, but I usually prefer not to work in Simulink, but for those of you who are interested, I will show you the diagram. Okay, so this is the final control law. U is equal to C times the square root of the absolute value of sliding surface times the sine of the sliding surface plus the integral of B times sine of sliding surface. B is a positive constant. B and C are the positive constants related to the sliding mode control, and in the experimental study they have just given the values of all the relevant constants, and they have given the value of the theta L that should be that can be used here. So for example, here as the theta L is basically given to us, which is a function of time, and based on this theta L we have torque reference, which is also given to us, which depends upon this value of theta L, and there are different values of frequencies for which the simulation has been created, and there are some graphs. You can see here that the reference torque and is following the actual torque, and the error is going to 0, and similarly here with PID control the error goes to 0 as well, but the error values are large. They go up to like plus 20 and minus 20. Here the error values they look like they're going to 0, but the scale on the y-axis is quite large, so I'm not sure if this is exactly 0 or plus minus 1 or something like that. Okay, so let's get into the action in terms of writing this. First of all, we need to write the state space system. This is the state space system of dynamic load simulator. So we will create a function. In this case I call this function stsmc_els3, so you can call this function anything, but you have to use these arguments, input arguments, and the output of the function. Then you need to write down the relevant values of the constants that are given in the table here. So we have this table, so here these kind of values are given in the table, and the frequency I use f is equal to 1. Then we have theta L reference value 8 pi over 180 f into sine of 2 pi ft, which is given here, 8 pi over 180 f sine of 2 pi ft. And then I have this t ref, which is also given here, 2250 f over pi into theta L ref over. So then I need the derivative. So computing the derivative of a sinusoidal function is very easy. The derivative of sine is cosine, and these 2 pi f will be multiplied with the derivative, so it's quite straightforward. You can also calculate the double derivative. I need this derivative and double derivative because if you go to the equations here in the state space, you can see here we need theta L double dot and theta L dot here, so that is why I have computed the derivatives here. And then I also need the t ref derivative, because t ref derivative will also be used later on in the control. Actually it is used here. You can see here that this t ref derivative is used in defining E2. Then we have these constants given in the paper. Actually the value of the C given in the paper is 45, but I am using the value 45,000. Well, the reason is simply because I tried the value 45 and it does not work, and 45,000 value works. So I don't know why this is, but that's what I found. So error E1 is tref minus x1 as given here, and tref derivative minus x2 is the E2. So notice that we have 3 state variables. First state variable is TL, second state variable is TL dot, and the third state variable will be the integral part in the control equation that I will show you in a few minutes. So continuing in this fashion, we have the sliding surface, which is E2 plus C times E1, and then we have the control given here. This is the control C times the square root of absolute value of S times sine of S plus x3. So x3 will be the state, the integrator state, whose derivative will be equal to b times sine of S. So this is how you implement integral control. I will post a link to the basics of integral control using MATLAB in the description of this video, so that the people who do not know how to introduce integrator state for integral control, they can watch that video to get familiarized. Then continuing, we have K2, K3, K4, K5. So these are defined up here in the paper. So you can see here that I don't need K1 here because I'm not going to convert this. This U is directly given in the paper, so I don't need U is equal to K1 times UM, unless the authors have made a mistake and there was UM. Actually this U is UM, and then I will need to multiply K1. You can try both things at your end. My job is to teach you how to write the code, and then you can explore different variations by yourself, hopefully. So then this phi and f of x I have combined. So this phi function, this is minus k2 x2 minus k3 x1 minus k4 theta l reference double dot minus k5 theta l dot, which we have defined here above by computing the derivatives of simple sine and cosine functions. Then we have the dynamics x1 dot is equal to x2, x2 dot is equal to u plus phi, which we have already defined, and then finally x3 dot, which is the integrator state of the control, that would be b times the sine of s. Then finally we define dx, which is this output of this function. And finally, and similarly, we can also write down the same. So this completes our code, and now we need to run this code and see what the plots look like. But before I go there, I just want to show you how to implement the PID control. So this is the same file as before, writing the constant values as given in the paper, theta, L reference, tau reference, derivative. These are all exactly the same code that we have already written here, so don't need to worry about that. So E1, E2 definitions exactly the same. The only difference is that instead of defining the sliding surface, we define the U control to be PID control, which is proportional gain. This is the proportional gain. I know this is very large gain, but small gains did not work, so I just randomly put in some numbers that work. I have not worked extensively on designing this PID control. You can go ahead and do some tuning of this control and get better results than I present in this video, and then that will maybe lead you to some sort of research contribution as well. That's my goal, to enable you to do research on your own. So this will be 500 times. So E2 is the derivative error, so that will be the derivative gain 500 and integral gain 2000. Again, I have just randomly put these numbers, and since these numbers work, so I don't tweak them or tune them to optimize the results. Then these are again K2, K3, K4, K5 are exactly the same as before, and phi is exactly the same as before, x1 dot exactly the same as before, x2 dot exactly the same as before. X3 dot before was b times sine of s because there was a sliding surface, but here the integrator state only needs to be the error. So the derivative of the integrator state is the error, and the integrator state itself will be the integral of the error. Then this completes the code of PID control. So now we have PID control of dynamic load simulator and the sliding mode control of dynamic load simulator, and we can compare these two controls using a script file. So in order to write the script file, this is the standard commands that I personally prefer to use. Clear all the command window stuff, clear all the previously defined variables, and close all the previously opened windows. This is the command that is used to solve the sliding mode control, this STSMC ELS3, which is the sliding mode control. So sliding mode control is solved for 2 seconds with 0 initial conditions, and the result will be stored in T1 and X1. Then I will use the similar command to solve the PID control, and the result will be stored in T2 and X2 with 0 initial condition and same in time interval. Then I define the frequency as the same as before. I have to define this theta L reference because I need to compare the reference value with the actual value. So tau reference, this is the same code that we have written in both of these files, except that here this is T1. This T1 will no longer be a scalar value. This T1 here, this here and here, this T1 is this T1 which will have a lot of data points. Then we have theta LR double dot as in the other file we defined, and tau reference dot. Then we have C and B, the same value as defined here in the sliding mode control. And then we have the errors. So I call E1 as E11 because there will be 2 types of errors. One is the error due to sliding mode control, and the other will be the errors due to PID control. So I need to compare PID with the sliding mode, so I define the errors in different with different subscripts. So sliding surface as before, E2 plus C times E1, except that E1 is now E11 and E2 is now E21. U1 is the sliding mode control, exactly the same as before, but here instead of using X1 so this is X1 all rows and the third column. That means that this will be all the data points that are solved that are obtained using solving this equation of the third state variable. And since this is in the equation of U, there we have a third state variable. Notice this difference so that you will know how to write the control system, get the control in the script file out of the function file. So this is the control, and now I need to redefine these reference values using T2 instead of T1, because this will be the reference value with the data points that are obtained by solving the other PID control based equation. So there will be T2 here, and notice that I have changed the names a little bit as well so that these variables don't clash with each other. And then we have this theta L reference double dot, and then we have tau reference dot E. So E1 is now E12 and E2 is now E22. And notice how I use X2 all rows and second state here, and X1 all rows and X1 all rows and second state here, and X1 all rows and first state here, and X2 all rows. And so X2 is the data points by solving the PID based differential equations, and this is based on sliding mode. Then we have U2, which is the PID control. We need to simulate this. Now in figure 1 I have 2 plots. Plot number 1 will be the TL from the sliding mode control, and then I will hold on and plot the reference for the same file. So I will see if the TL is tracking its reference or not. And then similarly in the second plot of the same figure, I will have the TL from the PID control, and I will plot it against its reference. So I will see this subplot will tell me if PID is working well, and this subplot will tell me if sliding mode is working well or not. So continuing in this manner, I will have figure 2. In figure 2 I will again have 2 plots. The first plot will tell me the time versus error E1, and and then I will also have time versus the other time T2 versus E1 of the PID control. So I will plot the both errors on the same plot, just to compare how these two errors relate with each other. Then in the second plot I will have E2 for sliding mode and E2 for PID control, and then in figure 3 I will have the sliding surface. That can only be for the sliding mode control, so I don't have sliding surface in the PID control, so this will be only one plot. And finally in figure 4 I will compare the control magnitude for SMC and control magnitude for PID. So that will be all, and that completes our code. So in complete code we have 3 files. You can see here this is the file with PID control. You should be able to write it by yourself after watching this video, and you can also take screenshot of this video and copy, literally you can copy paste this code. This is the sliding mode control code, and this is the code that we use to solve the ODEs and compare the different values. So we run this, and once we run this we will have a bunch of figures. So this figure 4 is the comparison of control magnitudes. You can see there that both controllers, sliding mode and PID, have almost exactly the same control effort applied to the system, which is quite astonishing. This is the sliding surface. It is oscillating around 0. It does not exactly become 0. Then these are the errors. You can see the error due to sliding surface, sliding mode control, that is the blue line, and error due to PID is the red dotted line. Error due to PID is slightly worse than the error due to sliding mode control, and this error both almost go to 0. But of course if we magnify, then maybe the picture will be a little bit different. So if we magnify here, so these are not exactly 0, so these are like, these have some values. So you can see here that the blue line is the error due to SMC and the dotted red line is the error due to PID. So same, you can, if you compare this this file, this, although this looks like error is going to 0, but I would assume that the error would be, I can further reduce this error by increasing the gain C, but I leave it up to you. So if you want to reduce this error any further, all you have to do is put another 0 here. Instead of 45,000, just use 450,000 value for C, then the error will be further reduced. And I have checked it, by the way. I'm not saying it just for the sake of argument. So these are the plots. This is reference torque versus the actual torque for sliding mode control, and this is the reference torque versus actual torque for the PID. It looks like they are, the reference following is quite good, although by looking at the errors we know that the reference following is not exact. But it's not visible here because the magnitude is from 100 to minus 100. So in the large magnitude, this is almost 1% error. So in terms of percentage, this error is 1%. You can further reduce it from 1% to maybe 0.5 or 0.05% by increasing the value of C. And again I want to show you for the different frequency, f is equal to 4. So if we want f is equal to 4, we have to do f is equal to 4 in all 3 files. So f is equal to 4 here as well, and f is equal to 4 here as well. So if I keep now I change the frequency and see if the reference is still tracked, and you can see the results are similar, although this is now high frequency. Again PID is slightly worse than sliding mode, but not too much. Error is again within 1%, and you can see here the tracking is quite good. So that is all for now. So that was the video related to the dynamic load simulator. I hope that it will help you in starting your research related to this topic, or if you are interested in super twisting sliding mode control. Stay tuned for the upcoming more video lectures on MATLAB simulations of control systems, and if you would like to stay informed, then you can subscribe and hit the bell icon It's really up to you. Thank you very much. Sorry, I almost forgot to show you the Simulink file related to this paper, which I promised you at the beginning of this video that I will show you the Simulink file which corresponds to this figure 3 of the paper. So the way you make Simulink file, first of all you type Simulink here. This is an old MATLAB, but you might have a newer version which only will make your life easier, not more difficult than, you know. Okay, so I've already created this, so I will open the model, this one. So you can see here that this is the model that I have created. It's a little bit messy, but it's the same thing that is shown here. Let's compare this side by side. So we have this model here and this model here. So you can see here, first of all we have this tau ref here, and then this is being subtracted from its actual value, and then we have this constant c, which is 45. You will have to use 45,000, I suppose. So this you have to multiply with the c will have to be multiplied with the error. So the error is coming here, it is being multiplied with c, and then c into error will go into this summation block. So c times error. This is the product block. All of these blocks are very common in Simulink. You can see here that you know commonly used blocks. You can get the gain, the constant, the integrator, and everything. And then continuous blocks, you can get this transfer function and so on. And mostly mathematical operation, you will only use one of the operations, like this math function. Here I have used for square root. So there are many math functions available here. So if you open this, there is like a there is square root, log, and everything. So you will be using the square root. So then this is really the same thing as here. So c into absolute value and the square root of the absolute value. So you will have to take absolute value first, and then you will take the square root of the absolute value, then you multiply it with the c, and then it will add up with the sine of s. So sine of s is coming here. These will be added. You can actually take a picture or screenshot of this diagram and then try to create it by yourself. Then you have this summation, and then it goes on and to add up with the integrator. So sine of s times b, that will be integrator state. So if you integrate it and add it, this becomes u. So at this point you have u, but you multiply it with some gain k1, I suppose. So let me check here. So this you have u, there you have u, and then you multiply it with k1 and divide by k1, and this you get um. So here after this gain we get um, and then this is again dtc is just a gain, and then you after that you have this transfer function. After the transfer function is integrator, and after the integrator is again the gain 1 over n. So let me show you 1 over n, and then there is you have to add the theta ref here. So theta ref is given in the paper. So this is a sinusoidal function like t ref, so you can give it here. So here you can see there this amplitude is 8 pi over 180, which is 8 degrees, and 2 pi is the frequency. So that's so then you can just run this file and see what happens. So that is all regarding this paper, and I just draw this just for fun. I usually prefer the other code that I have shown you in the earlier part of the video. Well, thank you very much, and best of luck with all of your research.